Okay, so, yeah, let's fill this out first. Basic log functions. All right, something goes in this blank, the general form of a log function. Okay, it's going to look like this. Y equals log base B of X. Okay, so the B, the base B is a little superscript and it's, subscript, and it's below the line, okay? Sort of the opposite of an exponent. It's down below, okay? And the thing about log functions is that there is not one true parent function because the base value can be different, okay? And I just went through my stuff and I found this notes that we did when we did exponentials, and it was the same thing. There was not one parent function. And this little table is what we kind of used, and we just plugged in whatever our base was for B. Well, for a log function, it's going to be very similar, except what we learned yesterday is that these two are inverses. So if I want to create a general table for any log base B function, I'm just going to switch the x's and y's in this table. And you know, for some reason, I did not put a spot for that on these notes. So I'm going to put that back here, okay? Let's just create a little space for this guy, log base B of X. Okay. And then to generate this table, all I'm going to do is take our exponential and switch the x's and y's. So all of these x's are now going to become my y's. This is similar to what you did yesterday on the Desmos activity. And then these are going to become my x's. So 1b squared, 1 over b, 1 over b squared. Okay? So this is just coming from the inverse of exponentials. And then whatever our base is, we're just going to plug that in for b. So whether that be 2 or 10 or whatever, we're just going to plug that in. Okay? But realistically, what I would ever ask you to graph, or at least understand graphs of, would just be any of these three. Okay? The most basic, base 2, base 10, that's your common log. Remember that from yesterday? Base 10 is your common log. And base E, that's your natural log. Okay? Whoop, what did I do? Okay. All right, so I'm going to come down here. I've got the three functions right here. I'm going to go to the table, okay? And this is going to be the table for log base 2 of x. So if 2 is my base, I'm just going to plug in 2 for b here, okay? So I'll just write my y's on this side. 0, 1, 2, 1, 0, 2, 2 squared is 4, 1 over 2, and 1 over 4. And yeah, there are more points than that, right? But that's just a good sampling of points. And that graph is already here for you. Like you could identify the points are right here, 1, 0, 2, 1, 4, 2. Okay, here it is. But what we notice is that there is an asymptote, just like there was an asymptote for exponentials. Exponentials had an asymptote of y equals 0. But for logs, since that's the inverse, it won't be y equals 0. It'll be what equals 0? X. So I'm going to draw my asymptote in, and this is x equals 0. So it's a vertical asymptote now. Okay? Intercepts, That's just asking us what's crossing an axis. So we have no y-intercept, obviously, but our x-intercept is 1, 0. That's this point right here. Okay. Now we got to think about domain. The domain, let me go back to 2 to the x. This one, the domain was all real numbers, and the range was 0 to infinity. Well, those two things are just going to switch for a log function. Our domain is 0 to infinity, because x is, this is like the wall, right? It can't cross or touch the wall. So our domain, 0 to infinity, or x is greater than 0. And our range, that is all real numbers, or negative infinity to infinity. Because this graph is going to reach way down forever and all the way up forever. Okay? So everything about this function just switched. Okay? Okay, taking a look at the other two, the second one is log x. Okay, that's our common log. So if we don't see a base, we know that that means the base is 10, right? So if I want to make my table for this one, I'm going to keep my same y's, and then I'm just going to plug in 10 into this table. So 1, 10, 10 squared, which is 100, 1 over 10, 1 over 100. So 1, 10, 10 squared is 100. Okay, so I'm not really going to have you graph this yourself too much, because you can tell these points get crazy real quick. Okay, but here's a picture of the graph. Now let's look at all of these things. Does it appear to have the same asymptote as log base 2? Yeah, right? It's approaching it faster, but it's still the same asymptote. So our asymptote, still x equals 0. We still have an x-intercept of 1, 0. 1, 0 is still on this function as well. Domain, x is going to be almost 0 to infinity, or x is greater than 0. And our range, that's all real numbers. Okay. And one last parent to look at. We're going to look at f of x equals ln x. Remember, ln means the base is e. Okay? The base is e. So when I come over here and I want to make my table, -2, -1, 0, 1, 2, I will be plugging in e for the b. Okay, and I know that that represents numbers, but we're not going to put the decimal because we don't need to. So this would be 1, this would be e, this would be e squared, this would be 1 over e, and 1 over e squared. Okay, and then we can see, oh look, it has the same intercept, 1, 0, as the others, same asymptote, same domain, same range. Okay, so what we've learned here is that even though we can have multiple parent functions, the domain, range, and asymptote of those will all match. Okay, so obviously there can be more, right? We could have log of base 3, log of base 1/2, right? But these are the three that we're going to focus on as far as the graphs. And as far as you making a graph, this is the only one I'm going to ask you to make a graph of because it's the one that has the nicest points, right? So what we're going to do now is take baby steps to investigate transformations, and we're going to do that with this function, okay? So we're going to go inside. We're going to do page 2. We're going to leave the last page for tomorrow, okay? Okay, if you have different colored pens, that'd be helpful because we are going to put 2 graphs on each grid, and having different colors just kind of helps. Okay? Okay, so it says the graph of g of x was obtained by translating the graph of f of x equals log base 2 of x to the right 2 units. Graph f of x and g of x on the same grid. Okay, so I'm going to pick a color. I'm going to use my plain dark blue pen. And I want to make this graph on this grid. Okay? Now, I didn't want to keep flipping back and forth, so I just copied down the table on a little sticky note so we can just easily grab these points. Okay? Once you do it a few times, you'll know it. You won't have to flip back and forth too. Okay? So let's just plot these points on this graph. I always like to start with the intercept just because it's the easiest point because it's always in the same spot. 1, 0, 2, 1, 4, 2. And then on the other side of my intercept, I have 1/2, -1, 1/4, -2. And that gives us enough to understand what's going on, right? We're going to, as we move to the right, it's going to increase, and as it moves to the left, it's going to go down and approach our y-axis, but it's never going to touch it. So I'm going to make sure that I draw in the asymptote and then connect my points and label this f of x. Always want to label your functions when you're putting more than one on a graph. Okay. Okay. So that's f, that's our parent. Now we want to graph g of x on the same grid. And how do we get g of x? It's this graph translated to the right 2 units. Okay? So how we're going to do that is we're just going to take each of the 5 points that we just plotted and we're going to physically move them to the right 2 units. Okay? So it doesn't matter what point you start with. Let's say I'm going to start with this one. I'm going to right 2. Well, I instantly went off the page. That's fine. Next point, right 2. Next point, right 2. So that's it. You're just shifting those points to the right 2. Okay. And then as you move those points to the right, something else is also moving to the right. What's moving along with those points? The points moved to the right, something else went with it. What went with it? Asymptote. Yeah, the asymptote also moved to the right. Okay? So I have to draw it again because it moved. So the asymptote for g of x is now right here. And I'm going to connect my points and be careful not to cross the asymptote. And I'm going to label that g of x. Okay. Now we're going to see what changed as far as the attributes of the graph. Describe any changes to the domain, to the range, and asymptote. Okay. So what we're just putting here is any changes that occurred to g of x. So let's start with the asymptote. Clearly the asymptote changed, right? On the parent it was x equals 0, and on g of x our asymptote changes to x equals what number? 2. So the asymptote changes to x equals 2, so that means the domain also changes, right? The domain is no longer 0 to infinity, but it's now 2 to infinity, right? Changes to, or x is greater than 2. Okay? And then the range. Are we still negative infinity to infinity? Yeah. So I'm just going to put no change. It's still all real numbers. Okay. So what we've just learned is that moving to the right changes the domain and the asymptote. Okay? All right. Now we're going to do something similar in example 2. Okay, so same parent function. And this time we're going to create g of x by shifting it up 3 units. So I'm going to grab my table and plot these points again to make f of x. Keep my colors the same. 1, 0, 2, 1, 4, 2. Okay. All right, and then to make g of x, we're going to take these points and go up 3 units. So just like before, to do that, take each point and just move it up 3. Each point, 1, 2, 3. Describe the changes. I'm just abbreviating domain, range, asymptote. Okay. So, moving up 3. Let's start with the asymptote. Does the asymptote change at all? No. No change. It's still at x equals 0. Okay. So if the asymptote didn't change, that means the domain didn't either, right? So no change, it's still x is greater than 0. And how about the range? Moving it up, did it change the range? But I got to look at where it's going. So it's going down forever and up forever. The shape is different, right? It is shifted, but what the y's are allowed to do is still go into negative and positive infinity. So this is going to have no change. So it's still all real numbers. Okay, so what we learned there is that when I just move the graph up or down, it does not change any of the attributes. Okay? Graph looks different, but the attributes are not affected. Okay, last one. Example 3, the graph of g of x is obtained by translating the graph of x, f of x equals log base 2 of x to the left 4 units and down 1 unit. Okay, so we're doing a mix of transformations. But first, we're going to get our parent on there one more time. 1, 0, 2, 1, 4, 2. And our asymptote. Okay, and to create g of x, we're going to move every point left 4 and down 1. Okay, so every point I'm going to move to the left 4 and down 1. 1, 2, 3, 4, down 1. This point, 1, 2, 3, 4, down 1. This point, 1, 2, 3, 4, down 1. This point, 1, 2, 3, 4, 1, 1, 2, 3, 4, down 1. Okay. Oh, I think I misplaced my first point. 1, 2, 3, 4, down 1, Genzer. It's right here. Misgraphed that. Okay, it looks like we have a new asymptote, right? Let's see where that is. If all the points moved left, then that means the asymptote also moved left, okay? So if I figure out domain range, changes to each of these things, okay, so moving left 4 and down 1 changed my asymptote. Changes to x equals, not x equals 0, but x equals -4. Right? Because here, go left 4. 1, 2, 3, 4. Here it is. Okay? So that means the domain also changes, right? Changes to parentheses -4 to infinity, or x is greater than -4. And changes to the range, well, there aren't any, right? Moving it up or down did not change the range at all. So no change to the range. It's still all real numbers. Okay? And today we're not going to worry so much about what these look like in the equation. That's coming tomorrow. Today is just all about understanding the attributes of the graph and what happens to those attributes when we move the graph left, right, or up, down. Okay? All right.